I have chosen two subjects for illustrating the type of work I have been conducted together with Yuri Gaidide and also other collaborators, including Peter Sørensen here at the Technical University of Denmark. And the two subjects are sine-Gordon solitons in curved Josephson junctions, which relates very nicely to the talk by Peter on curved DNA molecules. And then the second thing, this is a completely another type of physics, is acoustic shock waves. The work here have been, as I said, conducted together with Peter Sørensen, Yuri Gaidide as a very important and main contributor, Anders Rønne Rasmussen, Carlos Gorilla from Spain, and Jean-Guy Caputo from Rouen in France. The first thing, well, the actual content of this is that I would like to illustrate how clever Yuri was to do a collective coordinate approach for studying, for example, kink solitons in the sine-Gordon models for curved Josephson junctions, but also for other type of physical systems, including ultrasounds in thermoviscous fluids, where you don't have these Hamiltonian structures, but it's a dissipative system where you have a balance between dissipation and a nonlinearity, giving rise to coherent wave structures. In the sine-Gordon system, it's Hamiltonian systems where you have balancing dispersion and nonlinearity. So the type of curved Josephson junctions we looked at was this geometry here. The barrier I have shown on the right figure, and there's a straight line, and then there's a curved part, and then there's a straight line again. And the model for this is the sine-Gordon equation, which are written here, and we are actually considering a Josephson junctions which is so wide that we also need to take into account the direction perpendicular to the center line. So that is the y direction here. And then we have added damping. The boundary conditions at the sides here and here, that is at this place and actually behind here, we have boundary conditions, which is the normal of the boundary, and then the gradient of phi is proportional to the total current through the Josephson junction. This is also referred to as inline boundary conditions, and the energy input and driving force to kinks and solitons in the Josephson junction comes from this inline boundary condition. So what we did was we changed coordinate system. So instead of being in the Cartesian coordinates or rectangular coordinate systems, we went to a coordinate system expressed by S, where S is the position along the bent Josephson junction, and U is the perpendicular to the center line. So that's a coordinate perpendicular to the center line. So now we are looking at a straight strip instead of a curved strip. But in the curved region, we then modify the equation, or the equation becomes modified by this variable transformation from R with coordinates x and y to the coordinates x and u. And the modified sine-Gordon equation you see here, now we have a g function, which is a metric tensor related to the curvature, which I call kappa here, which is 1 minus u times kappa x, and then squared, that's GSS. And the g here is given by this expression here. You see 1 minus u, and then the curvature of S. And the curvature is on the straight lines are 0, so then G is just 1, and we have the original sine-Gordon equation. And in the curved region, kappa here is actually 1 over the curvature ratio R, if it's an arc circle, times U. The boundary conditions I have at the becomes also a little bit more easy, because it's then divided U is proportional to the current. So now we come to the way of treating or finding approximate solutions using collective coordinate approach. And there, Ulrich Ide, he was a great master. And with great physical intuition, he could reformulate the model in such a way that we could get very good approximate solutions. And in this case, we are changing the phase phi into two parts. Phi naught, which only depend on u, and then at psi, which depends both on S and U and also on time t. And the reason for using phi naught of U is to transform boundary condition into homogeneous boundary conditions for the psi here. So phi naught takes care of the inhomogeneous boundary conditions. Phi naught satisfy this type of pendular equation, and with a boundary condition that the phi naught du is proportional to the current I at u plus minus the width half. And if you insert that in the previous sine-Gordon equation, then you get an equation for psi, which is a little bit, well, I would say, somewhat more complicated than the original problem, but they had the advantage that psi now satisfy homogeneous boundary conditions. The next step is to make a traveling wave ansatz, and there we use the standard kink soliton, which is for sine-Gordon equation 4 arctan, and then the exponential of S minus some function capital S of U and T, and divided by B of U and T. S denotes the position of the soliton at time t. It depends now on U, that is the distance perpendicular to the center line of the junction. B describes the width of the soliton. B is a slow function of U. S is also a slow function of U, but S also includes the velocity. So the position is the initial position, let us call it S naught, minus some velocity B times T. And the velocity times T is actually a fast variable. The velocity itself is slow. I won't go through all the details, but just sketch what Yuri was doing in this analysis. He determined the Lagrangian density and integrate, and in the Lagrange density, we insert the solution ansatz, integrate over the fast variables. Then one gets the equations Lagrangian for S and B, where also S dot and B dot, that means the time derivative of S and B enters. Then you can fully expand S and B, and this is actually done down here. There enters as S naught and S1 times sine pi over W times U. So we separate variables. And also B is a Fourier transform. Actually, there are more terms, but they are neglected. In addition, S1 here is actually also neglected. And we assume, among further things, that S naught dot is much smaller than 1. That is a relatively slow velocity of our soliton. The Lagrange function can then be for S and B actually looks like this. It's T minus V, where T is the kinetic energy. So here enters S dot squared and B dot squared with some parameters in front. And this S, well, I just took it from our paper, but it's actually S naught of T, and S1 is neglected, as I was mentioning before. Then we get a very, well, it actually Yuri who obtained this pretty complicated expression for the potential. F here and capital U also are rather lengthy functional relations. In this expression here, the width is B1 of T. And I think an accomplishment of this collective coordinate approach is to find this B here, because then you somehow have a dynamics described by S and B, which is a kind of could be interpreted as two mechanical particles with positions S and B, and you can more easily interpret what is going on. The potential V, as we have a functional relation of the potential as function of S and B, we can plot, and here, as you see, it's pretty complicated, even graphically. Graphically, it's more easy to see what is going on, but even the graphics here, I think this is complicated. Now you can derive the Euler-Lagrange equations, which is down here. We just find the Euler-Lagrange equation for S naught and for B1. And it's second order differential equations, and they are coupled. Here's a cross-sectional type of picture of the potential for certain values of B, B1 equals 0, and for some parameter values, depending on the radius of curvature and the width of the junction, you get something, you could actually get such kind of barriers, simple barriers, but also on certain parts, more complicated barriers where you somehow have a trapping region in the middle. This could happen. So here you will expect that you could send in a soliton, for example, from the left, and it could fall down in this trapping region and stay there. Or, you know, you just have the simple barriers here. You know, if the soliton has too little energy, it will be reflected. If it has sufficiently high energy, it will actually be transmitted. And this we actually studied in more detail. Here is full numerical simulations of the situation for a soliton velocity 0.17. We see a soliton coming from the left, moving toward the bent region. It goes into the bent region. That means it climbs up the hill here, and it gets reflected. This is somehow already anticipated in the potential, which was calculated. Another thing is that you also see that due to the relatively wide junctions, the front of the kink is actually bent also. So there's a bending phenomena there. If the velocity is higher, then a soliton can be transmitted. I mean, it's simply passing over the barrier and through passes over the hill and into the second straight part of the junction. So here it's transmitted.
Mats, excuse me, please. What colors show on your figures?
It's actually the colors is the blue color is starting from 0, increases, and it's about pi here in the yellow-green part, and in the red it converges toward 2 pi.
Thank you.
Here's then a comparison with the collective coordinate approach, which Galilei developed, and the full curve here is full numerical simulations of the partial differential equation in 2D, and the dashed curves here are from the collective coordinate approach, these equations for S and B. And the collective coordinates approach is not completely far out compared with the full numerical simulations. And one nice feature is that they somehow predict for which velocities you have reflection and which velocities you have transmission. It is close to 0.2, this critical velocity between reflection and transmission, and the full numerical analysis and the collective coordinate analysis actually predicted very close to the same critical point. Actually, the critical point Euler was calculating was 0.19, and the full numerical simulation said it was between 0.18 and 0.19. I think that was pretty close. My second part here is on another type of model, is on oscillating acoustic waves in the tube, and it is acoustic waves in a thermoviscous fluid. Here there are some number of different variants of equation of motion called weak nonlinear acoustic wave motion, wave equations, and one of the very famous, maybe one of the first such weak acoustic wave model is by Kuznetsov in 73, as far as I remember. The way you derive them is that you take the equation of motion, that is in the Stokes equation of continuity, and now you include heat transfer, and this means you have an equation for the entropy. You also need an equation of state. So the heat transfer equation and the equation of state, that's somehow taken care of the thermoviscous part of the equation. And now you get a weakly nonlinear equation of this kind you see here in 1. You have a wave equation, and then with some nonlinear terms, and then you also have a dissipative terms in B here. So you can balance dissipation and nonlinearity and get shock waves. Psi here is the fluid flow velocity potential. And we look at the tube where we, at the left-hand side, has an ultrasound generator giving rise to a boundary condition for the fluid flow, which is minus psi dx, which is some constant sine omega t. And at the right-hand side, we have a fixed wall, so this means that the fluid velocity here will be 0. I should say that the pressure is proportional to psi t. Then at that time, my PhD student Anders Rønne Rasmussen, he conducted some simulations of the wave patterns you could see in the tube. Here is some numerical results for omega equal 2 pi. And what you see is that you actually see two shock waves. They actually counter propagating. And but if you look at the feature here, you see you have the shock wave, but then you have more or less straight lines outside the shock. And this is for the velocity. Galilei we were discussing this year with Euler and came up with this traveling wave ansatz for a collective coordinate approach. And in order to take care of these linear sloping velocity, then in psi, that is potential, we need quadratic terms in x and t, and not just linear terms in x and t. So we added these terms in A3, A4, and A5. The flow velocity now becomes minus psi x, which is this capital phi here, which is minus psi prime. Psi depends on the coordinate x minus x naught minus vt. There are now, after differentiation, we get linear terms in t and x, which we actually need for the slopes. And inserting this traveling ansatz in the weak acoustic wave equation, we arrive at an equation for phi, which is an ordinary differential equation of second order, nonlinear, which you see down here. And this is quite a lengthy type of equation. And actually, you can solve this equation. And Galilei did that, and he had a couple of transformation steps further, and could derive. I think it was in this case we arrived at this lambda W solution, lambda W function. But I won't go through that because it's pretty lengthy, and I will just refer to the references I showed on previous slides. There you can read about this. So what we did is that the equation for capital phi we solved actually numerically because all these transformations forth and back was a little bit cumbersome. So we just did it numerically, and this is the initial condition in, you see here as it's used as the initial condition for the solution of the full PD, weak acoustic wave equation, and this is the fat line here. And then the boundary conditions are constructed in such a way that they follow the solution of the equation for capital phi, this analytic solution for the collective coordinate approach. And actually we see a propagation here in the full PD numerical solution, which is stable and comply with the equation for phi. The velocity, I have to say, is given by this expression here, and this 0.75. We conducted some other types of full numerical simulation of this acoustic wave in a tube. And here you see you go from x equals 1, so the length of the tube is 1, and here you see a stationary state of true counter-propagating and interacting solitons. But on top of that, you have some nearly linear modes also. Here is a contour plot of the pressure, and actually when I'm measuring the velocity of these propagating shock waves, I see the velocity is not 0.75, but it's actually 1. So these solutions here I'm showing here is different from those we have from the collective coordinates. Now the propagating the two counter-propagating shock waves I showed before. That is at a resonance frequency omega equal 2 pi. So at equal 2 pi, we get two interacting shock waves. At omega equal pi, we get one shock wave. I'm actually currently doing some numerical simulation of that. But we could also do some simulations for off resonance frequencies as omega 0.1. And then I'm increasing the amplitude of the driver in order to see some effects. Actually, Yuri, he made a perturbation theory also on this case, which is presented in the papers I was citing before. I don't have time to go through that here, but I would just like to show this result, which I think is a little bit striking, because I got very surprised when I did the simulation, because I expected a nice sinusoidal type of wave propagation here of the velocity u as function of x and t. But what I observed was that on top of this wave propagation, nearly linear wave propagation, some very erratic type of waves also arrived, and it turns out to be shock waves which moves on the top of this linear wave or in conjunction with this linear wave very fast forth and back in the tube. And actually, to verify that they are really there, I made a magnification of these shock waves, and you see they are pretty nice running. So on top of these nearly linear modes, which Yuri he was able to calculate. You can also see this mixture between shock waves and nearly linear waves when you are just studying one resonant frequency close to pi. I've seen that. So my summary, if I should sum up on this work, I would say you can utilize the coherent structures of solitons or nearly solitons in perturbed systems, and also in shock waves where you have a balance between nonlinearity and dissipation. In both cases, you are having coherent structures which are very suitable for a collective coordinate approach, as Yuri was so clever in handling, and his mathematical skills here were magnificent. In this work here, in both cases, we validate the collective coordinate approach, and also there are limits to how accurate they are. But those things we verified by full numerical simulations. And then I will just finally say that Yuri Gaide was a great master of the collective coordinate approach. And this ends my talk, but I would like to show this one. This is Yuri in Les Choux in France in 2003. There was a conference there, a skiing conference, which we participated in. And let me just mention, Yuri was not only good in physics and mathematics, he was also a very clever skier, I may say. I was very surprised when we went out skiing here in the afternoons. So skiing sport is also one of the sports we have to add to the skills of Yuri. So thank you very much for your attention.
Thank you very much, Max. Thank you. Questions, please. So did I understand you correctly in the last part of your talk that the shock wave is riding atop of the linear acoustic wave?
Yeah, that's the way I interpret it. But you could also argue it's a mixture between a shock wave and linear waves, that they are both somehow appearing. And if you should treat this, for example, in a collective coordinate approach, maybe you should assume a shock wave plus some linear waves, sinusoidal waves.
Yes.
And maybe there are some kind of interaction between them, but that's, I don't know. They actually look that they are pretty much not interacting, only weakly.
Thank you. Very interesting.
I have seen it for simpler systems where I have just one, where I'm having omega, which is pi, where you can only have one shock wave going forth and back on top of these nearly linear waves. It's a little bit more easy to to show, and also a more simple type of systems.
And it reminds me also the soliton wave riding the linear tide wave when they
Yes.
come into the rivers, the
Yes.
waves. So
I think it's more or less the same type of phenomenon.
Right.
I
Thank you
will
very
agree
much.
with it. Yeah.
It's really very interesting. Other questions, please?
May I ask?
Yes,
question?
please. Professor Petrov.
My question concerns the applicability of the sine-Gordon model, especially when the coherent regime is discovered. There are any criteria to use sine-Gordon model for concrete system?
Well, for the, I have to admit, for the long Josephson junctions, I have not really seen any applications. You could maybe use it for information type of processing that you have in these solitons, and you can guide them around on long Josephson junctions. But the application of Josephson junctions is more on point Josephson junctions, where you just have where the barrier area is very small, and there you have numerous type of applications. For example, for standard volt standard measurements in metrology, this is used all over.
It is clear. It is clear.
Yeah,
it's not only model system.
Yeah.
I understand.
Yeah,
Thank
but
you.
another, I would like to add one. A couple of years ago, I was at a conference in Rhodes, island of Rhodes in Greece, where there was a colleague from an American company called Hypres, where they are actually building Josephson junction circuitries. And there were some people at IBM thinking about reviving the idea of making computers by Josephson junctions, because these new data centers you build, the high-tech companies are building around the world, requires a lot of energy. And as they are stationary in computers in big buildings, maybe the disadvantage of cooling things is not such big things.
Thank you.
Thank you. Any other question? Mats, thank you very much. And thank you for a wonderful photo of Yuri. Thank you. Now,
You're
could you
welcome.
please
Thanks. I will go out. I have to just
stop